Okay, I think we'll go ahead and start. Welcome to the I4Energy series. I'm Therese Peffer, Assistant Director of I4Energy, and I'm very excited to introduce today's speakers. I think you're in for a good talk today. I have one announcement, which is that it's a Twitter announcement. Citrus is now on Twitter at Citrus News, so please follow us there. At the end of today's talk, we will have a question and answer session. And our online webcast viewers, those of you on other campus viewing this, you can ask questions live via Twitter using the hashtag #Citrus, so that's CITRIS I4E. So you can also submit questions as usual through the Yahoo IM username Citrus Events. So without any further ado, I'll announce our speakers. Dr. Alexandra Sascha von Meier is the co-director in CIEE's electric grid program area. She's also the adjunct professor in in the Department of EECS here on campus. She focuses on power distribution systems, smart grid issues, and the integration of distributed and intermittent generation. Sascha is author of the textbook Electric Power Systems, A Conceptual Introduction. Until 2011, she was Professor of Energy Management and Design in the Department of Environmental Studies and Planning at Sonoma State University, where she taught a curriculum centered on energy efficiency and renewable resources. Her past research includes studies of cultural factors and technology adoption, operation of nuclear power plants, and management of nuclear materials. Sascha is UCB grown. She received her BA in physics in 1986 and a PhD in energy and resources in 1995. And Alex McEachern is president of Power Standards Lab in California, the founder of BMI, the former president of both BMI and Electrotech, and the author of many different publications, but including the Electric Power Measurements chapter of the Encyclopedia of Electrical and Electronics Engineering, as well as the industry standard Handbook of Power Signatures. Alex is active in drafting and approving international power standards. He's the chairman of the International Electric Technical Commission, TC77A Working Group 9, which sets the standard for power quality instruments. He participates in the drafting of the voltage dip immunity standards, IEC. I'm not going to pronounce all these things. Sorry. He's a senior member of IEEE, former chairman of IEEE 1159.9, a co-author of IEEE 519 and 1459, and a voting member of IEEE Standards Coordination Committee on Power Quality. So with that, I'm going to let them take over. They've got their tag team set up, so very good. Please join me in welcoming Alex and Sascha.
Thank you. Thank you very much. Well, good afternoon. Thank you for coming. Sascha and I are going to take turns on this a little bit, and I'm going to start by giving the background of this really new idea for a measurement technology that has great potential. So forgive me for starting at the very basic level, but we thought there might be students from other departments here that might be interested for one reason or another. So the electric power grid, which is what we're talking about, is used for moving energy from one place to another. You don't create energy with electricity. Electricity is just a transport mechanism. You usually don't use electricity. As Amory Lovins likes to point out, people don't buy electricity. They buy cold beers and warm showers. You know, and similarly, you don't make electricity. You make something that spins, and you use a generator to turn the spinning into electricity to move it somewhere else. Now, in the course of moving it somewhere else, you need to know just a couple of minor points. One is that the current is the flow of electricity. And it used to be in the early 1900s that the voltage was actually called the pressure of the electricity. So you had pressure and flow just like you have for water in a pipe, and they're pretty good analogies. And power, which is the rate that you're sending energy from one place to another, is more or less voltage times current. It turns out that all of the losses in power distribution systems come from the current, not from the voltage. The more current you push, the more losses you have. And it's more or less related to the square of the current, so it really is sensitive to how much current you're trying to move through the system. Consequently, to move a given amount of power, you want to do it at the highest possible voltage you can get away with to have the lowest possible losses. So if you're going to move power long distances, you do it at more than 100,000 volts. These transmission systems here are probably 350,000 volts, somewhere in that region. And that's what you use when you're going to move power more than 10 or so kilometers. Move power 100 kilometers, you use a transmission system, and you run it at more than 100,000 volts, which keeps the currents down in reasonable levels, hundreds of amps. But this is an expensive thing to do because you got to build these great big tall towers that have great big wide arms. So when you get closer to where you're going to use the electricity, you use a transformer, which is just a bunch of plates of iron wrapped with coils, copper coils, to step the voltage down and the current up. You get the same amount of power, but now you can run it around on these kinds of wires at 10 kilovolts, 12 kilovolts, 20 kilovolts, something like that. You do that for short distances, a kilometer, 2 kilometers, 10 kilometers maybe, unless you're in Australia, and then you might do it for 50 kilometers. They got long ways to go. What can you say? But now we're talking about smaller systems, pieces of wood that are only this long instead of pieces of steel that are all the way across this room. And it's less expensive, but of course the losses are higher for a given amount of energy because we're only doing it at 24,000 volts, so you have to have more current. You still don't want to bring 24,000 volts into your house. So before it gets to your house, it's stepped down one more time to 120 volts, 240 volts, something like that, and that's where you use it. You don't want to move that level of voltage more than 100 meters or so, or you just get tremendous losses from the current. Transmission, distribution, and what utility guys call low voltage, anything less than 1,000 volts. Okay? And the next one, there we go, thank you. All of the generators are joined together into a grid, and they all work together to put power into the grid. The grid that we're connected to right here for all these lights is the Western Regional Grid, which covers everything west of the Rockies. You can see California right there, and we're somewhere in here. And all the generators that are west of the Rockies are joined together. In North America, we have 3 grids. We have the Western Grid, everything west of the Rockies. We have the Eastern Grid, and we have Texas. And there's historical reasons for that, but Texas is a republic and highly independent, and sort of like Quebec and Canada. Here we are, though. All of the generators are spinning on this grid, and they're all carefully watching the local phase angle, the angle of their shaft with respect to the local voltage, and they are adjusting their phase angles up and down to put out the correct amount of power. There is no central control of the generators on this huge grid. They are all acting independently by watching the grid locally. It's a wonderful system of cooperation, and it turns out to work and be fairly stable. It does allow the frequency to wander up and down. This is the frequency up at LBNL. It's also the frequency everywhere else on the grid, and it's wandering up and down slightly. It's close to 60 hertz, but it wanders. Okay, next. This is what the generators actually look like. You can see a guy standing there, right? They're enormous rotating machines. As a result, these kinds of generators don't make rapid changes in frequency or phase. When that thing's spinning, it doesn't slow down or speed up very well. And that's part of what keeps the entire grid stable. The other thing that keeps the whole grid stable is load diversity. the chances that every load in the entire Western grid will turn on simultaneously or turn off simultaneously is nil. It's not going to happen. There are so many loads, so many different characteristics, it all statistically averages out, and that helps the stability too. Except when it doesn't. And when it doesn't is when there is some enormous disturbance on the grid, like abruptly losing the San Onofre generator, which is a huge nuclear source. This is an old loss. When there was that earthquake a couple of years ago in Mexicali, San Onofre jumped offline. And you can see the entire frequency of the grid jumped. The entire Western grid, wherever you measured it, jumped during that earthquake. One way to think of this is that if you have a stable system, the example I always like to think of is a child hanging in a swing. It's stable, it has a stable position, but the interesting thing is what happens when you whack the stable system. Boom, it oscillates and then goes back to its stable point. To determine how stable a system is, people often whack it. How stable is this wall? It didn't oscillate very much. You know, that's encouraging. If I did that to the side of the tent, it would return to the same point, but it might go back and forth. So what happens when you whack the grid really hard? And you get something like this. This is over the course of about a minute. You see seconds along the bottom, and you can see this oscillation of this particular grid. This is actually on the Texas grid. And the interesting thing here is that the vertical axis on this graph is an angle in degrees. It's the angle between voltages at two different locations on the Texas grid. And this tells us that from an angular perspective, the Texas grid isn't quite stable. A nice, clean, stable grid would go up and settle down again. This is a very worrying sign of instability on the Texas transmission grid. This angular issue so leads nicely into what we're actually going to talk about today, which Sascha is going to talk about, which is this concept called synchrophasors. And those are instruments for measuring these angles. And I have to admit that the first time I heard it, synchrophasors, the word, I thought of my sisters, who, when we were much younger, both were into synchronized swimming. And that sort of synchro made me think. And phasors, of course, led me to this thought here. So it's a very early synchrophasors, but Sascha's going to talk about more modern ones. So.
Our synchrophasors are set to stun.
There we go.
Let me, ooh, you know what? Haha, we have a sequence issue. We lost a slide. This is a different version of the talk. Okay. Well, we could, how exciting. Who knows what's going to be next? It's just like doing research. You just don't know what you're going to find. So this slide actually will help me explain what I want to explain, which is that in the AC system, you have essentially, to a first approximation, synchronicity at all the points. So across the entire Western grid, as Alex was describing, essentially the voltage is increasing and decreasing and going negative and back, all at approximately the same time. That's what we mean by synchronism. But it's only approximate because, in fact, the physics of transferring power from one place to another require that there be a slight difference in the timing between this voltage wave at different locations. So that's what we're referring to as the phase angle. Each of these sine waves has its own phase relative to whatever you call time zero. But what's interesting is the difference between 2 points. Now, that's physically related to the amount of power that's flowing through the transmission lines between any 2 points. So, for example, as Alex described, the generators are each pushing. They're pushing against a magnetic field, converting mechanical to electric energy. But some generators are contributing more power than others. And a generator, as it's contributing more power, pushing that into the system, it is going to have a slightly advanced angle in its physical rotation, which translates into a slightly advanced timing or phase angle of the voltage at that spot in the system. And approximately, it's the case that the power transferred between two nodes goes as the product of voltage magnitudes at those nodes divided by the reactance of the transmission line between them. And this is the important part, the sign of this angle delta that describes the difference. Now, you can think of this in terms of a mechanical analogy. That is, if you're trying to transfer mechanical power through a rotating shaft, or I found this picture of a well-made German torque wrench, you can sort of imagine turning at one end, and then that power gets transferred to a rotation at the other end. But the angle of rotation is going to be slightly different at the place where you're inputting power rather than where the power is being extracted. It's a very, very small difference, but in the electric system, ooh, see, now we get, that was going to be my first slide, and that's the slide, see, they're out of sequence. That's the slide about what we mean by a phasor, because a phasor, just to define the term, is a mathematical construct that's very elegant and convenient for describing the behavior of these sinusoidal waveforms. So we're visualizing the sine wave in terms of this rotating vector, this phasor quantity that's rotating in the complex plane at a frequency corresponding to the alternating current, the AC frequency, in our case 60 times per second. And then we can express this in terms of this complex quantity that has two variables in it, the magnitude of the voltage in green, which is the length of this angle, and the angle that describes the timing. So when we say phasor, we're talking about this mathematical object. So in a network, so this comes back to transferring the power through the system, at each node, and this is a very small example of an AC network here, we have only 6 buses. In the Western United States, there's on the order of 10 to the 4 buses. But at each node, you can describe the angle, and you pick one as the reference angle, because, of course, it's meaningless to say the voltage crosses 0 or hits the maximum at 3 p.m. That doesn't mean anything. But it's only meaningful to compare the angles to each other. So you choose one that's your slack bus. You choose one where you say, OK, this is where I start my timer. That's called angle 0. And then compared to it, there are different voltage angles at these different buses that correspond approximately to how much power is being injected or withdrawn at each bus. And there's also a different voltage magnitude at each, but we're not interested in that right now. Now, as a result, physically, what happens is this difference in voltage angle is driving power through the lines. And the power flows here in this particular example are there's real and reactive power. We're interested mostly in the real power right now. Those are the blue arrows. So those are the megawatts flowing in one direction or the other. Now, you can think of the voltage phase angle as really being the underlying thing that's driving this power flow. Except until about the 1980s, there was no way to measure it. In fact, without computers, it's hard to even calculate it, because as the students in my power systems class will discover actually about next week, trying to figure out what these angles are by hand is a very tedious process. It involves inverting matrices of the order of how many buses you have. And you'll be really glad that there are computers to do this kind of thing. It's interestingly not a closed-form solution, because what you start with are the power flows. Those are what you're given. You know how much power is being injected at one location or the other. You know how much power is being withdrawn. And from that, you have to go backwards and figure out, well, what are the voltage angles and magnitudes that create that situation? That's called state estimation. So you have to do this numerically, and our computers can now do this, but it's not obvious. And before we could really do that very well, power systems were operated essentially without knowing what those angles were. this is really like Todd Laporte used to say, the electric grid is an example of a system that works in practice but not in theory. And there was enough slack and stability in the generators to absorb the fluctuations and keep the system stable, even though operators didn't actually know exactly what those angles were that are really driving the system. Synchrophasor technology is a way to observe empirically at each node what those relative angles are. Now, to do that, obviously, you need enough resolution in the time dimension, right? Because if you're going to compare the exact zero crossing of the voltage at one node versus another, and you're talking about a very small number of degrees, where 360 degrees corresponds to 1/60th of a second, you need to be able to compare your time at those different locations so that you can make essentially simultaneous measurements. So each measurement has to be time-stamped. That only became possible with GPS technology. So what we have then as a result are these PMUs, which are phasor measurement units at different locations, collecting their time information from the GPS satellite, and in a phasor data concentrator, combining their respective measurements. And once you have the comparison from a number of different nodes, then you can start to try and draw meaningful conclusions about it. The goal, of course, is to give system operators useful real-time information. That didn't used to be so important when there was a lot of extra capacity in the system. There was a lot of slack and extra room on transmission lines to transport extra power. Generators had some backup capabilities. But as we're driving the electric grid closer to the edge of its performance envelope, if you will, it becomes ever more important for operators to be aware in real time what the operating state is. So essentially, so that they can know how far away they are from the cliff at any given moment, where the whole thing becomes unstable. They need to know that. Now, it actually took some time for transmission PMUs to take off. What was really required was the analytics to provide an interface between all these voltage angle data and some meaningful, actionable intelligence for operators. This is an area that actually I4 Energy Partners have been actively involved in. The Consortium for Electric Reliability Technology Solutions, CERTS, includes Lawrence Berkeley Lab, in particular Joe Edo's group, and CIEE has also been coordinating research that deals with developing the analytics and applications of synchrophasor data to make it useful and actionable for operators. Here's the California ISO's control room. So these are really the key consumers of the transmission PMU information today. Transmission PMUs in North America, as you can see, are spread out, but it really started in California here. Now, the kind of information that you get is a very important diagnostic that one hopes would keep you away from the edge of a cliff, as I said. This is an example of measurements in Europe just before they went over a cliff. And this was in 2006, where you see the angle separation. These units down here are degrees. And so this is actually a sort of a voltage phase angle profile map where you can see where a lot of power is being injected. And it looks like the wind was kicking up in northern Germany and Denmark, right? They actually would have liked to have shut some of those turbines off, but they didn't have a way to communicate quickly enough to reduce the power that was generated here, whereas in southern Europe, there was more power being imported. So there was a lot of power flowing from north to south. They had lost a couple of transmission links, so there was a big impedance between north and south. As a result, the angles pulled apart by tens of degrees to where the system would have become completely unstable had there not been relays that opened and said, this is too far, we're separating. And essentially, the European grid separated into different chunks. And some load was lost, and this was not a good day. We also had a big outage on the western United States. that year that was preceded, it turns out, by oscillations. And what operators at the time saw was their state estimation, their model prediction of how power was going to flow, and it predicted something nice and smooth like this. It turns out that, and actually this was measured with some early synchrophasors that was deployed in a research setting, but that the operators didn't have access to at the time. At the California-Oregon border, which is a very important path for importing power, where power flows from north to south, there actually were growing oscillations of power that, as you can see, are a classic underdamped oscillation. This picture always reminds me of the Gary Larson cartoon about what we say to cats and what they hear. But OK, we have a Mac to PC graphics issue. On the right side, this was supposed to be the Western United States map. And it was going to be the same scale as this one. You see the idea here? It looks really great on my computer, this graphic. But so you still get the idea, which is that in this network, there are characteristic frequencies of oscillations which are subsynchronous, slower than 60 hertz. So the north-south oscillation, which was the culprit in the previous slide, for instance, is at around 1/4 hertz. So once every 4 seconds, the power sort of sloshes back and forth. Now, you can't completely avoid having those oscillations, but what you really want to know is, are they underdamped or overdamped, right? You want them to be plenty damped, so that if that oscillatory mode gets excited, it's going to be immediately damped out. So one of these operator tools that I was talking about actually has this, if you see this little indicator, is actually looking at these particular modes. So this one is the 0.25 hertz. And you have a little faux analog dial that's in the green range, which shows the % of damping. And if it goes into yellow, it's caution. And what the operators have to do is they have to try to adjust power flows so that the damping comes back. How do they know which? Guess what? They have to learn that empirically. We try to model and simulate it, but in the end, you have to just try it out. And see sort of which changes in dispatch result in making the system more stable, more damped. And then if the needle goes into the red, you know that you're in an underdamped situation and you really have to make changes. So as a result, we're actually even more constrained in using our transmission grid, but it's good that we at least know where we are, because essentially this needle shows the operators where the cliff is. So now we get into the question of, well, what about distribution systems? This makes a lot of sense in transmission. We see that for reliability, having the visibility of what's actually happening electrically for the operators. I've heard this described as, before synchrophasors, operating the grid was like driving down the freeway with your eyes closed. And maybe every 4 seconds, you got to open your eyes for a moment to see where you were. And with synchrophasors, it's like driving down the freeway with your eyes open. Much better. It's obvious that we need this for the transmission grid, but why for the distribution grid? Not obvious, but we think there's significant promise. And I think I'm going to turn this over to Alex now. I mean, just starting out, transmission PMUs are still on the order of 10,000, tens of thousands of dollars. That makes a lot of sense as a diagnostic device if what you're protecting is an area with many megawatts of customers served. At the distribution level, the business case is not as obvious, right? It's also more challenging to actually see what's going on, because the phase angle separations at the distribution level are going to be much smaller.
OK, so actually, is this microphone working? I don't think it is, because I can't seem to make it go green here. So I'm going to try. Does this one? Oh, this is a good one.
Mine is red.
Well, there we go. I'll use this. This is number 4 to the nice man. As Sascha was saying, one issue is you typically have tens of thousands to hundreds of thousands of dollars flowing through these wires on the transmission system per hour. On the distribution system, you're lucky if you have a few $100s flowing through per hour. So the value, I mean, one way to think of these wires is they're delivering power in one direction, and they're pipes full of money flowing back in the other direction. And then there's either analogy, either way works. But the amount of money in these pipes, much smaller. The other challenge on distribution is that, as Sascha said, all of the phase angles are introduced by the inductance of these conductors here. And the inductance is roughly linearly proportional to the distance between the conductors. And it's an order of magnitude bigger here than it is there. And it's roughly linearly proportional to the distance of the conductors. And again, you got an order of magnitude more distance here than you have there. So the inductances we're dealing with on the distribution system are a couple to 3 orders of magnitude smaller. So the phase angle differences we're talking about are also 3 orders of magnitude smaller. 1/1000th of a degree is interesting as opposed to a degree out on these systems. The third point is that it used to be we could always say the power flows from the substation to the load on the distribution system. It only flows one direction. Transmission system, it goes this way, it goes that way. But on the distribution system, it goes out towards the load. That isn't true anymore now that we have so many photovoltaic systems, so many small wind turbines, all those distributed generators. The other thing we used to be able to say is that the distribution system is stable because power flows from here to there, and that's it, nothing complicated. Now there are indications that it's becoming less stable, although we don't really know. Oh, I wanted to make one comment about this slide, because I just love seeing things in graphs that the author didn't intend to show you. You remember Sascha said that when you're measuring phase angles, you arbitrarily pick one point as 0 degrees. Doesn't matter which point. And then everything is measured relative to that physical point. In Western Europe, where did they pick as 0 degrees? Paris. You betcha. Paris is the center of the world once you start getting into this general region. Also, you notice that Great Britain has nothing to do with the European power grid. And they don't. They're completely separate. Anyway. So here's our idea that we're working on very hard right now. We call it a micro-phasor measurement unit. And we're trying to reduce the cost of phasor measurement units, these little instruments, by an order of magnitude to 2 orders of magnitude, that kind of range. And we're doing that by piggybacking it on an existing instrument. This is the little new PMU piggyback here, and this is its GPS receiver up here. And you can sort of get a sense of the physical scale. Previous PMUs were the size of the top of this lectern. This thing is the size of my fist, more or less. And doing this, these existing instruments are also power disturbance recorders. They're recording voltage sags and swells and impulses and frequency variations and changes in the waveform. And we think, but we don't know, it'll be interesting to combine the phase angle measurements to tell us about stability with these disturbances. A really critical point, a big cost in these phasor measurement units installations is the communication channel that you have to have open all the time back to the phasor data concentrator. And that communication channel is not inexpensive. It has to be running constantly, and it has to carry a fairly large amount of data. And to get that kind of communication channel on a distribution system would be very difficult. So we've designed this so that we don't need a communication channel. We've also done a lot of work, and the patents are still in progress, to get millidegree resolution as opposed to a degree or 1/10 of a degree. And that's what it's going to take to measure this kind of data on distribution systems. This is just a fascinating graph that Sascha put together for that conference in Portugal, right? Anyway, a while ago, a year ago. 2 years ago. And on this scale, you have logarithmic time. And these are all the different kinds of things that go on the power grid. For instance, Temperature and humidity changes on the order of a minute or so. There's a single cycle. When you're measuring frequency and how often you measure the angle, it's about once a cycle. Sags and swells, you're interested in half a cycle. Here's a degree, here's a tenth of a degree. GPS, the global positioning system, people generally think of it as a system that can tell you where you are. It turns out it can also tell you what time it is everywhere, easily within a microsecond, and with some work within hundreds of nanoseconds. And then you get all the way down to the clock accuracy on the phasor measurement unit itself, which is down in the couple of nanosecond kind of area. So huge range of interesting features that we're going to be storing in the micro-phasor measurement units. For those of you who are interested in the instrumentation, there's a really interesting challenge, that when you're doing power quality disturbance measurements, it's really important to get 2 to the n samples per time interval, typically a cycle or 12 cycles, so that you can do all sorts of harmonic analyses without any kind of bleeding over the edges when you do a Fourier transform. If you have 2 to the n samples in the time interval, that's very, very useful for doing the analysis. But the frequency changes all the time. So your frequency of your sampling algorithm has to track the frequency of the grid so that you always get, let's say, 512 samples per cycle. You have to be tweaking it up and down constantly. When you're trying to make synchronized measurements between 2 different locations, you want to do exactly the opposite. You want to do sampling based on time, not based on local frequency. So there's a sort of a challenge between the power quality measurements and the phasor measurements that has to be resolved. Now, remember Sascha said that the traditional PMUs, phasor measurement units, out on the transmission system constantly transmit their data back to a concentrator that provides the phase angle to the system operator. What we're setting up are these little tiny micro PMUs over here. We'll put one there, and we'll put one there, and we'll put there. And those, we're setting up a thing called a micro-PNet for gathering the data from all of them, using some interesting wireless techniques that have been developed here at Berkeley. That will be really useful. In the initial case, it's not even necessary because we'll be storing the phase angle measurements locally and gathering them up in other directions. But over the term of this project that we're planning, this will become the way that we gather together all of this distribution level data. So, Sascha, you're going to finish this up?
Sure.
Great. There we go.
Thank you, Alex. So this is an area that we thought, gee, at I4Energy, we have just the right team to work with someone like Alex and Power Standards Lab to try, as Alex has said, to build and test and implement this kind of sensitive measuring device. And we have one funding application submitted. We're going to see. I can't tell you any results yet. But we have an idea for the research that we'd like to do. And Alex has described sort of this idea of the micro-PNet. And really where it starts with is making empirical observations on distribution feeders, because nobody has ever looked at voltage phase angle on distribution circuits that closely before. So ultimately, we're interested in the question, does voltage phase angle lend itself as a state variable for understanding the dynamics of distribution circuits? And what can you do with it? And we believe that there are both diagnostic and control applications. There are other researchers who have written about this and speculated about what you can do with it. There's still very limited use of distribution level angle data, and nobody can really measure the angle separations in a meaningful sense between nearby locations on a circuit. So this is a nascent field that we're hoping to make a contribution. I'm not going to go through the list of applications except to say that there are obviously diagnostic applications for how a distribution circuit is behaving. There are possible control applications down the road in the future. And really, I think what's important is that there are problems that we know about now that could potentially be addressed with these diagnostic capabilities. In the future, we think that understanding power flow at the distribution level in terms, explicitly in terms of phase angle and the dynamics, and being able to observe very short-term kinds of behavior, being able to observe stability, transients, is going to give us essentially a different way of looking at the system, and is going to open up a host of new control options. So you could get creative with how you aggregate and coordinate and really recruit toward service for the entire grid your various distributed resources. Different applications are going to have different requirements for measurement accuracy. They'll have different requirements for communication speed, how much data you need to transfer. Clearly, there's some diagnostics that you can do just by looking at archival phase angle data. And there may be applications where you want as real-time, as close to real-time as possible. So there are a host of interesting questions that we look forward to exploring about sort of what's entailed here and what's required. For starters, we don't even know what are we going to find. Right? And this is really the case for distribution systems that, you know, surprises can be anywhere. We think that the basic observations, which way the power is flowing, as I said, transients, oscillations, also the specifics of how inverters are responding to oscillations or other changes on the grid are things that we can actually observe by measuring very small phase angles. And it's possible that looking at voltage angle in the distribution grid is like watching paint dry. That might happen too. We believe, though, that there are going to be some interesting things we find. We don't know for sure yet what it will be. That's why it's research. So with that, we have a few minutes for questions. Yes?
One would suspect that the inverters on solar panels are going to give you a rather nonlinear sine wave. And I wonder if, you know, lots of harmonic distortion and clipping, whatever. I'm wondering, is that going to affect your calculations on how you do the phase angles?
Well, yeah, I mean, it's an interesting question. First, it won't affect the calculations because you extract the fundamental from whatever they're delivering. And that's what you use for measuring you do a Fourier transform, so you eliminate everything except the 60 hertz component of whatever they're delivering. But I think a more interesting question in this context has to do with how rapidly those inverters can change their phase angles as they're trying to behave appropriately. You know, unlike the huge generators, which simply don't change their phase angles very rapidly. They do it very slowly because they got all this inertia. Electronic inverters don't have any phase inertia. So they're going to be leaping back and forth. And that may contribute to instability. Maybe it doesn't. We don't know. We're looking forward to finding out. Yeah, that's where we're at.
Well, I mean, I was just thinking also that the inverters, if they have a lot of high-frequency components to them, the effective inductive reactance of the lines might play into it. But you say that just as long as you convert it back to 60, it doesn't really matter.
Yeah, I think that's probably true. That it doesn't. It's true that it doesn't really matter because what we're primarily interested in here is the power flow, which in general, takes place at 60 hertz. There's not much power flow going on at the other frequencies due to the distortion. There's just, I mean, it's several orders of magnitude smaller. So I think that's the case.
Other questions?
Great, thank you. That was a great talk, by the way. So, one question: is there any way to model some of this? Are there simulation models or other modeling tools that can be help us to answer this before we actually do the measurements?
Yes, you can model power flow on distribution circuits, and in fact, there are a number of applications that are trying to do just that. The trick, of course, is that to know that your model is giving you correct answers, you have to validate it. And it's also the case that with more distributed energy resources and different kinds of components on the circuit, some of these models are having to be updated to account for the behavior of, for instance, the inverters that were not traditionally part of a distribution power flow package, the standard analysis of power flowing outward to the loads. So I think model validation is a really important part of getting these data. And naturally, you want to combine the empirical measurements with a model that predicts what they should have been, and you compare notes. But that's a very good point.
Thank you.
A lot of this reminded me when I took electrical engineering in the 1940s. And there was a transition from it being power to electronics. And one of the things was when we were doing power, it was very easy because we dealt only with amplitude modulation. And then when FM came, the world was quite very different. Probably the worst thing for many students is the math changed to where it was nice math, to where you got into, I forget even now the name of the math that went with FM, and it wasn't clear were you talking about FM or phase modulation. And getting the two of them separate and understood was very, very difficult if you had gone all through AM. And it was tied up whether the math had linear functions or there were functions that multiplied together. Like if you add sine A to sine B, that's easy. You don't get any new frequencies. Or you multiply sine A by sine B. You're in a different world, and you have to go back to kindergarten.
Thank you.
We look forward to kindergarten.
Yes. Just to extend that thought slightly, when you start going deeply into these phase angle questions, the difference between phase angles changing at different locations and the frequency changing at different locations, they're essentially the same concept, just looked at from slightly different perspectives. It turns out that phase angles are a useful way of looking at power flow. But obviously, to advance a phase angle here relative to here, the frequency must be slightly higher than it is here than here for a brief period of time. So you're right, it gets very complicated.
Are there applications of this with on the transmission grid? Because you're getting much higher resolution, and in the graphics you showed of the existing ones, it seemed fairly sparse distribution of the existing phasors.
You know, that's a good question. I think, to my knowledge, first of all, the really important phenomena that, at least that we know about today on the transmission grid, are observable through phase angle separations on the order of degrees. You know, and you see in the extreme situation that we showed with big power flows, you have tens of degrees. But as far as I know, the important oscillation modes, for instance, are phenomena that you can observe very effectively with the kind of angle resolution that today's instrumentation has, which was essentially developed for that purpose. Now, would you see anything else on the transmission grid if you looked at finer resolutions? I don't know. There's another question, which is, even if you saw something, would it be actionable information? In other words, would there be actions that you could take in response to that information? And that's, I think, as important as can you read and interpret the data, but is there something that you can then do about it? And we don't know yet.
It's a great idea, though.
Yeah.
I'd add one more sort of, I don't think we've ever sort of thought about this very much, but we're going to now. Thank you. But whenever you measure something on the measure voltage on the transmission grid, you have to have some sort of sensor to get the 350,000 volts down to something that you can measure. And in general, I'm not certain when we're talking about thousandths of a degree how those sensors behave. I just don't know. But it's a really interesting idea that we haven't thought of. Thank you. You've made it worthwhile. It's great.
So just one question on kind of related, but one of your slides mentioned nanosecond clock resolution, and I didn't see anything that talked about how does this micro PMU get its clock. I noticed it has GPS, but obviously that's not going to give you that fine-grained resolution. And then
that's correct. Kind
of related to that, how does do you have some sense of what sort of density you have to put out to these to get sort of accurate, or an accurate number, a large enough sampling to be able to do some of this analysis?
First, I apologize for the confusion on that slide. We actually have two different clocks we're talking about. The GPS clock is hundreds of nanoseconds kind of range. There we were talking about the clock inside the microprocessor that's doing the measurements and that is doing the timing of the digital signals, and it has nanosecond kinds of 2 nanosecond kind of resolution. Two different clocks. And so we do not have absolute time down to the nanosecond. We have absolute time down to hundreds of nanoseconds. Regarding your second question, do we know what the density requirement is? No. We don't know. We hope to find out. Yeah.
One last question? Okay, let's give a final thanks to Alex and Sascha.
Thank you.
Thank you.